In this video, we're going to talk about something called the alternating group on n elements, which we will call A sub n. So the group we're about to define is going to be a subgroup of S sub n. Here's the definition. A sub n is the group of even permutations in S sub n. And that's actually it. That's the entire idea. That's the whole video. No, just kidding. Because there's this word here. I said A sub n is the group of even permutations in S sub n. And by that I mean the group consisting of all of the even permutations in S sub n. Now, if I say that that's a group, I'd better prove this. Alright, so in this video we're going to prove that A sub n is a group, and we'll talk about its relationship with S sub n. Alright, so let's first prove that A sub n actually is a group. Alright, here we go. Well, what do we need to show in order to prove that A sub n is a group? We're going to use the two-step subgroup test. We could actually use the one-step. It wouldn't be that much of a burden. In fact, it might be a little bit shorter, but I like using the two-step subgroup test. First of all, we need to establish that A sub n is non-empty. That is not the empty set of permutations. For this, let's just observe that epsilon, the identity permutation, is an even permutation. This is because we can write epsilon as a product of no transpositions. And I'm putting this here, this little parentheses 1, because that's just a way that we sometimes write the identity, because it's awkward to write an epsilon equals and then nothing on the right side of the equals. But we are able to write epsilon as a product of no transpositions at all. If we multiply nothing, then what we have is the identity. If you don't believe in that line of reasoning, then consider this. We could also write the identity as the product of a transposition with itself, any transposition. And as long as n is greater than 1, that would work. So you'll notice we're able to write epsilon as a product of two transpositions. And if we can write it as a product of two, then by what we covered in the previous video, we can never write it as a product of an odd number of transpositions. It's always going to have to be an even number. All right, so epsilon is an even permutation. All right, so that shows that A sub n is non-empty. Now, what about showing that A sub n is closed under the group operation, which is still composition of permutations? All right, so let's suppose sigma, let's call them sigma 1 and sigma 2, are elements of A sub n. So these are both even permutations. Now, again, what it means to be even is that I can write each of these as a product of an even number of transpositions. Now here I go again doing 1 first. We should start with 1 on the right. There we go. So sigma 1 is a product of an even number of transpositions. And sigma 2 is also a product of an even number of transpositions. We'll call that mu s through mu 1. With s even. And just for making sure that what we see in the video is complete here, these are all of these, the taus and the mu's, are all transpositions. Important to say that at some point. Okay, so now, well, what about sigma 1 times sigma 2, or sigma 1 composed with sigma 2? I'm actually going to compose in this order, even though the same reasoning would work the other way. I need to show that sigma 1, sigma 2, or sigma 2, sigma 1, I guess I still read out loud from left to right. I need to show that this is also an even permutation, and therefore belongs to A sub n. So sigma 2 times sigma 1, that's going to be, well, the product of all of the mu transpositions times the product of all the tau transpositions. And, well, what do we have here? We have S of them, that is S transpositions here, and we have R of them, R transpositions here. So altogether, we have S plus R transpositions. S and R were both even, so their sum also is even. So we have the product represented as a product of an even number of transpositions, and therefore sigma 2, sigma 1 is also an element of A sub n because it can be expressed as a product of an even number of transpositions. Okay, so we know that A sub n is closed under multiplication. Now what about inverses? That's the other step that we have to do in order to complete the two-step subgroup test. So here's the proof of that. Suppose that sigma is an element of A sub n. All right, then sigma is even. So sigma is equal to some product of an even number of transpositions. I'm going to reuse the symbols tau because I don't want to come up with another Greek letter. I got tired of that in the previous video. So for some transpositions, tau 1 through tau r with r even. So now we need to show that sigma inverse also is expressible as a product of an even number of transpositions. And at this point, you should maybe just pause the video for a minute, let me stop talking, and see if you can figure out why sigma inverse would be expressible as a product of an even number of transpositions. So I'll just wait for you to pause the video and think about it. I guess I shouldn't wait while recording the video. You can pause the video and then I can just keep talking. So I'm going to keep talking now. The inverse of sigma, as we discovered in the previous video, is just all of these transpositions written in the reverse order. You can actually verify that if you multiply this product by this product, you get the identity, because in the middle you're going to have tau 1 times itself, and since it's a transposition, it's going to cancel itself out, and then you've got tau 2's together, those will cancel out, and so on. So this is also an even permutation because it's an even number of transpositions represented here. It's the same number. So sigma inverse also belongs to A sub n. Beautiful. So because A sub n is closed under composition and inverses, and it's non-empty, it's a subgroup of S sub n. And at this point we might ask, how big a subgroup is it? How many elements does it have? Because you'll remember that we said that the order of the group S sub n was n factorial. S sub n has a total of n factorial permutations. So a good question is, how many of those are even? We'll talk about that in the next video.